quantum mechanics collapse. It's all in the book. What's the problem? Theorists often claim that when a wave function collapses onto a molecule or atom in measurement, it does so instantaneously and indeterminately. I'm going to show you the alternate physical description, which takes place over time and which is in principle determinable. I'm going to start with wave-particle duality, electromagnetism, Maxwell's equations, and in particular an oscillating dipole produces a wave group which is got the electric field in the vertical plane, the magnetic field in the horizontal plane. They're entangled, they're out of phase by 90 degrees, but they have two velocities. Sometimes these velocities are different, sometimes the same. One is the group velocity and one is the phase velocity of the wave. This can be described by this expression, which contains a particle part and a wave part. This is the exponent of this wave group. We're going to go through Planck's law, de Broglie's momentum relativity, and look at the diffraction of crystals, particularly at momentum quanta, which are easy to visualize and understand and have a very important application in collapse. Here's our plane wave, wavelength lambda, frequency f. What's the velocity? Lambda times f. That's the plane wave, and that's the phase velocity. What is the momentum? We think of a bubble going round in an oscillating pattern here, up and down, leftwards and backwards. What's its momentum? What's the momentum of the water in the wave? Well, we're going to go along with de Broglie for the moment. The momentum is inversely proportional to lambda, but that's opposite to the physics we had here. Momentum is proportional to mass times velocity, and it should be proportional to lambda according to the simple model. So what's the solution? We're going to find that the momentum depends on the group velocity, not the phase velocity. And we're going to do so by studying relativity first. Let's go for a simple example to a piano tuner, two strings with slightly off-note phase. When we superpose the wavelength, we get a carrier wave and a beat wave with a beat frequency, and the piano tuner tries to get rid of this beat. The beat is trigonometric, but when we interpret it as a Gaussian, because the Fourier transform for Gaussian is a Gaussian, we find that the beat velocity turns into the group velocity. And this is what contributes to the momentum. So let's go on to relativity. Einstein knew that the speed of light is the same in all directions from previous experiments, and he knew that it was independent of what speed he was going when he measured it. Why? Because it depends on physical laws. And he deduced that the physical laws are invariant in all inertial reference frames, and that is the principle of special relativity. He deduced, furthermore, that E equals mc squared relativistic mass, which can be analyzed into momentum and rest mass. Applying Planck's law and the de Broglie hypothesis, we can, by substitution, find that omega squared is k squared plus m squared. K is the angular frequency, omega is the angular frequency, k is the wave vector. This is an interesting formula because m separates into a particle part and a wave part. But let's differentiate this because we get an even more important result. The product of d omega by dk plus omega over k is equal to c squared. What's omega over k? We saw that before. That's the phase velocity. And we've just seen that d omega by dk is the group velocity. So the product is equal to c squared. Illustrated here. At low velocities, the group velocity is Newtonian. The energy changes by half mv squared. But according to relativity, it limits at c as it goes faster and faster. So that's the phase group velocity. What's the phase velocity? The inverse. It gets very large at long wavelength and low energies. Here is the relativistic mass. I've described this diagram further in other videos in my channel, so we'll move on. Well, what is the angular frequency and what is the wave vector in terms of energy and momentum? We can get that from the formula in special relativity. You remember E squared is equal to mc squared, rest mass squared, plus p squared. This is a Pythagorean relationship. And E is equal to the rest mass energy plus the energy of the electron gun, which we get from the voltage of the gun. We know all these numbers, so we can plot the wavelength and frequency. This has been done millions of times in the last 100 years, so we know the answer very well. Vp times Vg is equal to 1, is equal to c squared, as we calculated, and the phase velocity is greater than the group velocity, especially where the energy is low. In the relativistic region, the phase velocity is equal to the group velocity. Just a slight diversion, but important. We can get from this formula the uncertainty. It's roughly the full width half maximum, and it turns out that you can derive from this the uncertainty in time, the uncertainty in energy by the Fourier transform, and the result is dt b omega equals 8 and dx dkx equals 8. These are slightly larger values than Heisenberg's limits, whatever they are. And they're well known. Fresnel knew them 100 years before Heisenberg, and he knew that in the near field the wave function collapses, and in the far field it expands. Where Heisenberg's limits are in all this, it's difficult to say. Well, we're now going to go on to describe momentum quanta. And momentum quanta particularly in quasi-crystals. We're going to look at crystal diffraction and go on to study Quasi-Bloch waves with dual harmonies, and they're very important in condensation. First of all, X-ray electron diffraction in crystals. The probe is periodic, the crystal is periodic, the diffraction pattern is periodic. And notice 0, 2, 4, 1 and 3 are missing. They're forbidden lines. We'll come back to that as we go along. The quasi-crystal is completely different. The probe is periodic, but the diffraction pattern is geometric. Here are the indices: 0, 1 over tau, 1, tau, tau squared, tau cubed, tau to the fourth. That is because in this hierarchic structure, the unit cell can be described by these golden rectangles with edge ratios 1 to tau. And that gives an edge ratio for the cluster, the icosahedral cluster of clusters, 1 plus tau, tau squared. So the stretching factor is 1 to tau squared. That's very important, and we're going to come to that again in a moment. This structure is uniquely aligned and uniquely icosahedral. What's the evidence for it? Well, part of the evidence for it is from Bursell and Peng. This is a phase contrast optimum defocus image and of aluminium 6 manganese, and it's in reverse contrast. So here's manganese, here's the unit cell, here's the cluster, which is 2 planes of 5 clusters, and here are 5 planes on 5 clusters on 1 plane in the supercluster. So we have 4 orders of hierarchy in this, and the hierarchical structure is infinitely extensible and uniquely icosahedral. Here's a stereogram of the principal axes of this icosahedral structure. And normal to the principal axes are the diffraction planes. In crystallography, it's well known that diffraction takes place on planes of atoms. Something similar happens in quasicrystals, but it's not quite so obvious. Anyway, the planes are perpendicular to the principal axes, and they are all three-dimensional, geometric, simple and complete. Dimensions should not be multiplied without necessity. Here's a simple image of Bragg diffraction and quasicrystal diffraction. In Bragg diffraction, the spacings between planes are unique for any particular Bragg diffraction. And if you look at the red rays, the first order, the difference in path length between these two rays is lambda. And the green rays are second order, 2 lambda. That's how Bragg diffraction occurs, and the wavefront is planar. In quasicrystal, it's much more complicated. There are multiple interplanar spacings, as we saw in the previous slide, and the wavefront is all jumbled up. It shouldn't diffract at all, but it does, and we're going to see how by calculation. Well, we can't calculate by Bragg's law. It doesn't apply. The order's wrong. But we can use the structure factor method. This method is used to explain why those forbidden lines were obtained in the crystal diffraction pattern. What we do is take a unit cell, project each atom in the unit cell onto the selected plane normal, the selected index, and sum the phases. If half the atoms are in antiphase with the other half, then you'll have a forbidden line. Otherwise, you will have a stronger line. That method is constantly used in X-ray electron crystallography. And we saw an example. To measure the structure factor in quasicrystals is slightly different. We make 2 adjustments. Firstly, because our unit cell is not periodically repeating, we have to sum over the whole quasicrystal, and we do this iteratively using the stretching factor tau squared, and introducing also a coherence factor. We do this because we know that wavefront is jumbled, and we don't know what CS to start with, but we're going to find out, and it's going to be very surprising. Meanwhile, we're able to measure using CS, as a calculated CS, or computed CS, we're able to measure the quasi-lattice parameter of that golden rectangle, and it turns out to be almost exactly the same as the diameter of aluminum as it should be. This is a experimental verification of both the method and the structure. Well, what is CS? The first thing you have to notice, and you can easily prove it by the mathematical induction, that tau to the power m is the same as this Fibonacci sequence: 1 tau, 1 plus tau, 1 plus 2 tau, 2 plus 3 tau, etc. And that's true for all integral m. This separates into a natural part and an irrational part, and you can approximately rationalize this by substituting part for 3 tau, and then you can substitute the rational part from the irrational index and find a metric function. Here it is, and it has a very surprising property, 2 very surprising properties, or even 3. It's the same for all the diffraction beams in the icosahedral structure, hundreds of them, and it's the exact inverse to several figures of the CS that we calculated by computation using the structure factor method. And it's the same for all m, t minus a half. It has this value 12% different from the comparative Bragg angle. CS is related to Bragg angles and to the effect of despacing. So we're able to go forward and think about Bloch waves in these quasicrystals. They are observed as they are in crystals. They're very well understood in crystals, and they're used to image crystal lattices, lattice images they're called, in crystals, the blue wave, and they're periodic. And they're periodic with the atomic planes in crystals and so on. But they're not periodic with the quasicrystal quasi-lattice, which is geometric. However, very strangely, when you expand the Bloch wave by the metric function that we previously calculated and measured or computed, when you expand that blue wave, you find the Quasi-Bloch wave, and this has very surprising and very important consequences. It's commensurate with the quasi-lattice, both long-range geometrically and short-range linearly. It's dual harmonic. And what it tells you is that all quanta are caused by harmonic resonances, certainly momentum quanta, but by extension all quanta. And we can go on to the conclusion, which is to do with condensation. What happens in condensation is the time-dependent group wave passes through a Young slit, and if the measuring instrument is transparent, the wave will simply be refracted through it. But normally the measurement is absorptive, and then the wave will resonate over time with the absorbing atoms, and one atom will dominate owing to hidden variables, and with resonance will absorb energy from the incoming photon or electron, absorb energy, and at the same time resonate with an annihilating photon. The photon will be annihilated, and the energy will be absorbed by the atom, which takes the measurement and converts it either by a scintillation or optoelectronic multiplication in a photomultiplier tube. Well, that's a physical explanation of how condensation occurs in time and with a possible determinism, which can, in some instances, be measured. The conclusion is, dual harmonies in quasicrystals demonstrate all quanta result from emissive harmonies, collapses due to resonant harmonies with photon annihilation, physical constants are hidden variables, math is chosen, physics is never weird.